Welcome to the 1406 Lab Flow workshop. Today we will look at the experiment compounds and their bonds. Our objective today, when we finish this workshop, you will be able to write an electron dot or a Lewis symbol and a Lewis structure for an atom and an ion. What is a Lewis structure? It's just a representation of a molecule showing all the valence electrons. At the end of this workshop, you will be able to write formulas and name ionic compounds. Also, write formulas and names for molecular compounds or covalent compounds, and after doing the Lewis structure for any molecule, you will be able to predict the shape of that molecule and decide if that molecule is polar or non-polar. This is a lot of information. Some of the information you already seen it in lecture, but I will make sure we will go, first of all, we will look at the write-up of the experiment, and then we will go directly to the report to make sure that you can do each step of the report, and we will do some practice of that. Stop me, I understand this is a lot of information. This is about 2 chapters. So I would like you to, this is the time to ask. I would like you to stop me anytime that you have a question. I'm here just to answer questions. This is not, I won't grade anybody. I will just help you get the maximum amount of points in your pre-lab quiz and in your report. And then at the end of the workshop, I will stay to make sure that you can, if you want to ask me an individual question, you can ask me that as well. Okay, so let's get started. Let's go over the write-up of the experiment. The first thing that is talking about is the ion formation. What is an ion? I know some of these you know and some you don't. So what is an ion? I believe that you know. Is when an atom gain or lose electrons. Gain or lose electrons. And here they are giving an example of sodium that becomes an ion, a positive +1 ion, and another example here that is an anion. When it's negative, we call it anion. When it's positive, we call it cation. And oxygen. I'm assuming that you know why the oxygen becomes -2. But just in case, let's share a periodic table and understand why an ion becomes +1 or why an ion becomes -2. So let's look at this periodic table. You see this periodic table. You will need to get familiar with the periodic table because this is going to be, I don't want to say Bible, but this is going to be your guide in the whole, I would say, semester. But the first chapters, you need to be familiar with this periodic table. The periodic table is arranged in this manner for a reason. Is arranged in this manner for many reasons. I won't go in detail because this is not a lecture, but I will give you the minimum information so you can complete your report. So when we look at these groups, group 1, group 2, at this point, you know that each element tries to have the electronic configuration of the noble gases. These are the noble gases. The noble gases have actually, right up to here, the noble gases have a configuration of 8 electrons in the outermost shell. Everybody wants to copy the noble gases because they have lower energy and they are more stable. So let's look at sodium. That is the example that they are giving us. First of all, we need to know, okay, sodium is in group 1. When we look at the example here, we see that this number 11 is the atomic number. What is the atomic number? Atomic number is the number of protons, and if it's a neutral atom, it's going to be the number of electrons as well. And this is very important because the number of protons gives you the identity of the metal. See how they are organized. Row 1 here, row 1. Okay, hydrogen, atomic number 1. Helium, atomic number 2. So the sodium wants to have the electronic configuration of the closest noble gas. Which one is the closest? Sodium is 11. Neon is 10. Neon is the closest noble gas. It has 10 protons and 10 electrons, which means that sodium has to lose 1 electron in order to have the electronic configuration of the neon. So when it loses 1 electron, it's going to be +1. Electrons are negative. So you don't have to think about this all the time, but you do have to know that if the element is in group 1, it's going to lose 1 electron. All these elements have end with 2s1, has 1 electron in the outermost shell, and it's going to lose that electron. So all this group 1 is going to be +1. The charge of group 2 is going to be +2. And then all these are transition metals, can have different charges, the ions. And here, the noble gases, we said no charge. They don't react. They are already stable. What happened with the groups, this group, the halogens? What happens with this group? This group is going to have a charge of -1 because chlorine, let's look at chlorine, this one. Chlorine is number 7, okay? So the closest noble gas is argon, that is number 8. So it needs to gain 1. If it gains 1, electrons are negative, it's going to be this group -1, oxygen -2, nitrogen -3, and this group, carbon, they don't lose much or gain much because 4 is, you have to gain 4 or lose 4, so we won't consider that a charge. So now let's go back to our write-up of the experiment. So they are giving us this example of sodium. We said that sodium loses 1 electron, and what happens? We said that in the nucleus, we have 11 positive charges. Around, we have the electrons that are negative. If it loses 1, what happens? In the nucleus, I have 11 positive, but around, I have only 10 electrons because one is lost. So 10 positive are neutralized by 10 negatives, but there is one positive that is not neutralized. That's why it becomes an ion and it has a positive charge. Any questions there? Okay. So let's continue then. And then they are giving you an example of the electron configuration. I'm assuming that you learn from a lecture how to write the electron configuration. I can go over later if you need it. So when we look, okay, so let's do it right now. How to write the electronic configuration of sodium. It's very simple, but you are going to need it because this is the basis. If you don't know how to write the electronic configuration, then you don't know the charge, then you don't know a lot of things. So let's share again the periodic table before we continue. Okay, we are back to our periodic table. How do we write the electronic configuration of any element? This is key. Ask me if you need it. Stop me anytime. First of all, when we look at the periodic table, the first thing that we have to see is these numbers. 1, 2, 3, the rows. This indicates the main energy levels of the atoms. And then we have the groups here. Group 1, group 2. Those elements in each group have the same chemical characteristics because they all have one electron in the outermost shell or 2 electrons. They have similar electronic configuration. So let's start for one easy. Let's say I ask you, give me the electronic configuration of beryllium. First thing I do, look at the atomic number. What is the atomic number of beryllium? Let's find it. Group 2? Yes, very good. So we know, because the atomic number is 4, we know that we have 4 protons and 4 electrons. We have to place 4 electrons in the, that's all we have, only 4 electrons in the atom. So we start by row 1 to the left. This helium actually is placed here, but think that the helium is here. It's much easier if you think like that. So this is the S block. And this, because you are non-major with the S and the P, I think you will be fine. This is the P block, right? So when you have to write the electronic configuration, you think that each box, each element like this has 1 electron. See, 1 hydrogen is 1. 1 more electron, helium. 1 more electron, lithium. So if we have to write the electronic configuration of beryllium, we always start from the upper left, always, and row 1. And we know this is the S block, so we start 1, S2. Let's review. Why 1? Because we are in row 1, the main energy level. Why S? Because we are in the S block. That's the first the first subshell that is going to be filled. So the first two electrons are going to the S block. The S, let's call it orbital, but I'm not sure if you are into that. But orbital S, yeah, let's call it orbital. So 1s2 in the S. It's an orbital that is circular. You can put up to 2 electrons in the S orbital. So we go, but we have to place 4 because beryllium has 4. So I finish with the 1. Very good. And I will go to the row 2. And I have to stop exactly where the element is. So I have to write a 2 because this is row 2. And then I am in the S block. All this group 1 and 2 is called S block. So then I would say 2 because I'm in the row 2, S, and then I have to stop at the beryllium, 2s2. So those little numbers, 2 and 2, when I add all those numbers, 2 plus 2, 4, has to equal the atomic number. Any questions? We will look at, can we do one further down? Of course. Let's do the sodium that they give us, or let's do aluminum that is here. I don't think you are going to be with, this is called the D block. I don't think you need that for this report. This is the D block, and this is the P block. But let's go to aluminum. What is the atomic number of aluminum? 13. Very good. So we know that we have 13 electrons to locate around the nucleus. Very good. So what is the first thing I have to write? I start from row 1 to the left. Always start with 1s2, right? Then I go to 2 here, s2. And then I have to always go horizontally until I finish the row 2. And then this is the P block, which means orbitals P are filled. I don't know if you went into the shape of the orbitals. We are not going to get there because that should be lecture, and then we have to, unless you want me to go at the end, I will explain what does it mean, the orbitals and the shape of the orbitals. But for our purpose of completing this report, I will continue explaining that this is the P block. Orbital P has like this shape, and you can have up to 6 electrons in the orbital P. It's hard to see. Let me erase this. It looks horrible. So orbitals P, you have the Px, Py, and Pz. So basically you have 6 electrons in the P block. And look, 1, 2, 3, 4, 5, 6. Okay, so let's go back to our aluminum. We had aluminum. Very good. And we said 1s2, 2s2, 2p6, because we start here, we finish 1, we go to row 2, y2, s, because this is the s block, y2p, because I'm in 2, row 2, and I am in p. And then I go to 3, 3s2, and then I have to stop in aluminum. Only one, the first element in the P block is aluminum. So I will go 3p1. Now I count. How many total electrons? 2, 4, 10, 12, 13. It matches. I stop there. This is the electronic configuration of aluminum. Since I'm here right now, I will show you something. How many are the valence electron? How do I look at the valence electrons? This is important. Valence electrons are the electrons that are in the outermost shell. Those electrons are going to participate in bonds, or they're going to form ions. So let's look at aluminum. How many valence electrons do you see? Which one is the outermost shell? So you look at the number 1, 2, and 3. Which one is the highest number? 3. 3 is the highest number. So that means that the outermost shell is everything that has a 3 because it's the highest number. Now you count the electrons. How many electrons you have? 2 plus 1, 3. So the valence electrons, aluminum has 3 valence electrons. Any questions? How to write the electronic configuration of any element, and how to decide which one are the valence electrons. Okay, so let's continue then with the write-up of the experiment. So now it should be a little clear. They give us the example of the sodium. We saw how to write. They give you an example, Electron Dot Symbol, and they write sodium dot. What is the Electron Dot Symbol? Is just to write each one dot is one electron. And why does it have the sodium only one dot? Because when you look at the electron configuration, you look here at how many valence electrons do you have? So you look 1s2, 2s2, 2p6, 3s1. You look at the highest number, and it has only one electron. Very good. Then I have just one dot. And that is the electron that is going to be lost. And that's why the sodium is going to become sodium plus. Let's continue. Oxygen, same concept. It gains 2 electrons to achieve the closest noble gas configuration. And then when you have to write the electron dot symbol, you just put the number of dots. As we said, one dot is one electron, but only the valence electron. Is just a convenient way to keep track of the valence electron in an atom. So here you look at oxygen, we look at the highest number, 2s2, 2p4. So we have 2 plus 4, we have 6 valence electrons. Then we write 6 dots. Very good. So they are giving us the example. Then they start with ionic compounds. Before we proceed, you will learn how to write a formula of ionic compound, how to name an ionic compound, how to write a formula of a covalent or a molecular compound, and how to name it. But you need to know, when you are given a formula, you have to know first if it's ionic or if it's not ionic. Why? Because they are named in a different way. So first thing, look and decide if it's an ionic compound. So let's look at here again. Let's look at the periodic table. Everything that you see in yellow are metals. An ionic compound is a compound formed, is a bond between a metal and a non-metal. That is very important. It's an electrostatic attraction. It's a bond between ions of opposite charges. So when you are going to decide if it's ionic or you will look, see in the periodic table, the majority of the elements are in yellow. So basically, ionic would be, if you have boron, boron is shown as a metalloid or a semi-metal. So it's not a metal, it's not a non-metal. So basically, non-metals is, the others are even, this one, we said are the noble gases, are not going to react. So we have only a few non-metals. So ionic compounds are between metals and non-metals. So this is the first thing you have to look. When you are given two elements to name or to form or to write a formula, look at the periodic table and decide if first thing, if it's a metal or if it's a non-metal. Very good. Once you do that, you will look at the charge. So they are helping you here with this chart that we already looked at. They're saying, okay, if it's group 1 in the periodic table, the charge is going to be +1. If it's in group 2, the charge is going to be +2. And they are saying that the compounds are neutral. And how do we name these compounds? Basically, let's say we have this compound. Easy, the easiest. This is table salt. So the first element is sodium. The second element is a non-metal, is chlorine. And here we name first the positive, sodium, and then the negatively charged ion. So the ions are named, if they are cations, they are named the same way as the element. So sodium, sodium. The chlorine changes the ending. Instead of chlorine, it's going to be chloride. That's why we call this element sodium chloride. You notice that we don't use prefixes because it's an ionic compound. Let's continue and look at the write-up. Then they are talking about metals with variable charges. So we know that group 1 will always have a +1. Group 2 will always have a +2 charge, but all the transition metals in the periodic table may have different charges. They can lose, let's look at iron. Iron can lose 2 electrons, or depending on the case, can lose 3. So then we have to write in the name the Roman number. So when many times I receive a question on when do I use the Roman number? You use the Roman number when it's a transition metal that you cannot predict the charge. And then they are giving you exceptions. Here you will need to know that all these 3 elements, zinc, silver, and cadmium, you don't have to write the Roman number, because zinc is always going to give you a +2. So learn these 3, silver +1 and cadmium +2. And then there is another exception that in this case, they are transition metals that already have 1 possibility and 1 ion. And here, there are 2 elements that are tin and lead that are not transition metals, but we still have to put the Roman numbers. These are the only exceptions, because lead can sometimes be +2, sometimes +4. So then we need to write the Roman number. But those are the only exceptions. Any questions so far? Okay.
Yeah, actually, I do have a question. It's a little bit long to write out. How am I determining which form iron's in, I guess? How am I going to know if it's 2 or 3?
Okay, then that's why you need the Roman number. And actually, what they are saying is that for this is only an exception. So you will know, because they will have to write the Roman number. Let's say I have a compound that is this one. And I ask you, what is the name? If you said lead chloride, it's wrong, because you don't know if it's this compound, or because we said that the lead can have +2 or +4. So the lead can form these 2 compounds. This one if it's +2, and this one if it's +4. So if I ask you what is the correct name, you will have to say lead, in Roman numbers the 2, and then chloride. Did I answer the question?
Yes, so any time we're supposed to determine the numeral or the Roman numeral of it, it will have the +2 or +4 in the equation. Is that correct?
Right. If they give you the equation, from here, if they give you the formula, you know that the lead in this case is +2, right?
Right.
Because you know that chloride. So you know that this compound is +2. So if I give you this formula and I ask you, what is the name of that compound? How are you going to write? You're going to say the name is lead,
parentheses, Roman numeral 2, chloride.
Exactly.
Okay.
Exactly. But this is an exception, because lead and tin are not transition metals. And so this is an exception that we have to add the Roman number. That is correct. And also they tell you, like, let's say I have this compound. I give you this formula and I ask you, can you tell me the name of this? And you are going to say silver chloride without the Roman number, because that's another exception, that even though silver is a transition metal, silver always gives a +1. So these are exceptions. You don't have to encounter them that much, but all the others here, iron, manganese, they all add here iron to ion, iron to bromide, because they are transition metals. And here they are just giving an exception. That's it. So basically, if you remember that lead and tin, you have to add the Roman number, you are good to go. And if you memorize the charge of this one, these three, you are good to go, because you don't need Roman numbers. Silver always is going to give you +1, even though it's a transition metal. Did I answer the question?
I think so.
Okay. And here they are giving us examples of polyatomic ions. What are polyatomic ions? Unfortunately, you will have to memorize. There is no way. You will have to memorize the most common. Here it says multiple elements are bound together and they have a charge. So they are ions that are going to behave as a unit, same way as if they are an atom, but they are a group of atoms, like ammonium here. This is, if you see more than one atom with a charge, is a polyatomic ion. And you will have to memorize the most common. I'm sure you already did for lecture, most of them. So here they are giving you the names, and so you will have to remember those names, because if I tell you what is the name of this compound, I give you this formula and I ask you write the name, you will have to know that this is a polyatomic ion that has one negative charge and is called nitrate. So the name of the compound is sodium nitrate. We don't have to change the ending for IDE because it's not one atom, it's a polyatomic ion. But we'll see all the examples in the report. So we'll go over all the exercise that you have to do. And now, okay, so here it says, if more than one polyatomic ion is needed, the polyatomic ion formula needs parentheses. So, like if I ask you, okay, what is the compound that, write the formula of the compound that is made between barium and phosphate. You are going to write, because the phosphate is a polyatomic ion, you are going to write barium 3, and then you need a parenthesis, because you have to treat the polyatomic ion as one. And when you are going to write the subscript, that is a 2, if you don't put the parenthesis, will mean that it's only applied to the oxygen, to the last atom, but you need to make sure that the 2 applies to the whole phosphate. So that's all it's saying here. And then they are telling us how to write when do we have a molecular compound or a covalent compound. So when you are given a compound, let's say this compound, when I look at the periodic table, fluorine is a non-metal and nitrogen is a non-metal. So we have a compound between 2 non-metals. So this is not an ionic compound because there are no ions. Metals, when we have metals, they tend to lose electrons. But the non-metals have a tendency of gaining electrons in order to achieve the noble gas configuration. So if I have a bond of 2 non-metals, both want the electrons. Nobody's gonna release electrons like the metals. Then the solution is sharing the electrons. Sharing the electrons. So this line, this bond between the 2 atoms, implies that there are 2 electrons in that bond that are shared between the 2 atoms. And we will go over how to write the Lewis structure. This is a Lewis structure. It's basically a representation of the molecule, including all the valence electron. This is what the Lewis structure is. And I can go over step by step because some students want to just write the bonds and they forget the lone pairs, and that will give you the wrong shape of the molecule or the wrong polarity. You have to learn how to do the Lewis structure correctly, so all the rest will come correct. And then how you name molecular compounds. The naming molecular compounds is much easier than naming and actually the ionic, but that's what I think. You basically use prefixes. So you have to learn all these prefixes. If the formula carbon monoxide has 1 carbon and 1 oxygen, the first atom never you don't use mono, which is 1 for the first atom. So it's carbon monoxide. So you use the prefix. If it's 1, if it's 2 atoms, you use di, tri, tetra. But I believe, have you seen that in lecture? Let me ask you so I don't teach something they already seen. Oh no, okay. That is scary. Okay, so okay, so let's learn the basic to complete this report. So we said that ionic compounds, we saw how to name it. Now when we have to name a compound between 2 non-metals, we use prefixes. So you have to memorize the prefixes. If you have 1 atom, it's going to be mono. If you have 2, it's going to be di or di. So let's look at this compound, S fluor 6, and I name this compound. Let's say in the test, you see this compound, and I ask you, what is the name? First thing you're going to do, look at which elements are involved in that bond, in that compound. And you're going to say, oh, both are non-metals. Then I have prefixes in order to name it because it's a molecular compound. And then you look at, okay, I have one sulfur. I don't have to use mono at the beginning, only in the second atom. And I say, okay, sulfur, which is the name of the first atom, and then I have 6 fluor. So I change the ending to, instead of fluorine, I change to IDE. And I use the prefix hexa, which means 6. So it's sulfur hexafluoride. So I always going to use this system when it is a compound that is a covalent compound. And then it's a lot of information. So we are getting to the end of the write-up, and then we'll practice a lot while we are going to look at the report. So let's see what you have to learn. You have to learn how to do the Lewis structure. That is very important. And they are giving here an example on how to do the Lewis structure of CO2. So do you want me to go over on how to write a Lewis structure? Or you are familiar with that? Okay, so let's go over to how to write a Lewis structure. And let's first do the example that they are doing. So let me share the whiteboard. Okay, so they are using, I will say, okay, give me the Lewis structure of CO2. Okay, first thing you do, go to the periodic table and tell me how many valence electrons are in carbon. Tell me that. You can message me. Which group is carbon? Look at your periodic table and tell me
E.
how many valence electrons. Sorry, I couldn't. How many?
Is it 13 in P block?
I couldn't hear. It's in the P block. In which group? How many? I'm not very good. 14. Okay. So what Taylor is telling me, what are you? You are counting everything. I just asked you for the carbon. How many valence electron has the carbon? Look at the carbon in row 2. Which group is carbon?
I mean, I guess it's group 14 or 4A.
Okay. Let's ignore. Okay. Let's okay, group 14. The group 14 has how many? Let's write the configuration of the we need to learn how many valence electrons are in each atom.
Okay.
So what is the electronic configuration?
That's what we did at the beginning of this.
Let's write the electronic.
Okay.
Okay, so let's look at the electronic configuration of carbon. 1s2, right? 2s2, and now what? 2p what?
And then 2p2.
Very good. Now, how do I know how many valence electrons are there?
So we look and see that 2's the highest number in S and in P. So we take the 2. So the 2s2 and the 2p2, we add those two together for the 4.
Very good. So what we are saying is that carbon has 4 valence electrons, right? 2 plus 2.
Correct.
Very good.
Okay.
These are from the carbon. But because I have a molecule that is CO2, I need to count the valence electrons for all the atoms. So let's look at oxygen. How many valence electrons I have?
We have 8, I believe.
8 valence electrons. Let's look at the electronic configuration of oxygen. Oxygen, we do 1s2, right? 2s2.
It's not 8.
And then we do 2p what?
It would be 2p4.
Very good. And now we have to look at the highest number.
So 2 plus 4.
And exactly. So I have the oxygen has 6 electrons. You will get familiar, and you probably won't need to do this every time. You will remember that the group 1 has 1 valence electron, the group 2 has 2 valence electron, and then you ignore the transition metals and you go to the group that is the boron, the group of the boron and the aluminum, and you're going to say it has 3 valence electrons. And then the following group has 4, the carbon. You will remember by looking at getting familiar with the periodic table, and you will know. But if not, you can do this, what we just did. So now we have 2 oxygens. So which means we have how many total valence electron in this molecule? We have 6 valence electrons for 1 oxygen.
And
so we have 6
oxygen
plus 6 plus 4. Everybody agree with this?
Yeah, makes sense.
So we have 16 electrons total. This is how the first step when you have to write the Lewis structure. Then what you have to do is the first element in the formula is going to be your central atom. And it because it's a molecule, it has to be bonded somehow. At least we start with 1 bond. And then, because we needed 2 electrons for this bond and 2 electrons for this bond, from the 16 electrons, we have to subtract 4. If you have 12 electrons now left from the total valence electrons, you start placing, you never start in the central atom. You always start around. So you have 12, and you have to make sure that each atom completes the octet. We said that the 8 electrons is a very stable electronic configuration. Everybody wants to complete the octet. So if I have 12 and I add 1, 2, 3, 4, 5, 6, and another 6 in the other, I used all my electrons. I don't have any more. And now I have to look if each atom has an octet. Each bond shared counts as 2. So oxygen has 6 here, 3 lone pairs, plus 1 bond makes 8. The other oxygen the same, but carbon, how many electrons have carbon? The way I draw this Lewis structure. 4, very good. And it has to have 8. Somehow the Lewis structure is not complete, and they have to borrow, they have to share. Carbon says to the oxygen, hey, you have the octet and I don't. So they will share, and that is when you have to do a double bond. So basically, the structure is going to be this. These two electrons are going to be shared instead of being a lone pair. So the oxygen will end up with only two lone pairs, and it's going to be a double bond. This is the correct Lewis structure. Everybody has the octet, and everybody. Now they are going to ask you, since I'm here, if the molecule is polar. What does it mean that the molecule is polar? And they are going to ask you the shape of the molecule. This is the last part. So when is a molecule polar? Everybody, who can tell me when is a molecule polar? You know that each atom has different electronegativity. They are sharing electrons here, right? They are sharing electrons. But when you look in the periodic table, what is electronegativity? Is the tendency to attract electrons. It's like if I am pulling from a rope, and another stronger person, a quarterback, is on the other end and pulling there. And we both pull. He's so strong that he's gonna bring me to that area because it's so strong. With the electronegativity, each atom has different tendency of attracting electrons, which means it's going to be closer. We write it this way here, a bond, but the electron density is going to be closer to the most electronegative atom. In the periodic table, the tendency as you go this way, as you go to the right in the periodic table, as you go up, the atoms are most electronegative. I don't think you need to know that, but you need to know that carbon and oxygen has different electronegativity. And because the oxygen is toward the right, the electron dense, this bond, carbon-oxygen, is polar. But because there is another bond here pulling in the other direction, the molecule is not going to be polar. Polarity is a concept that is difficult to grasp. I would say when you have to decide if a molecule is polar, let's do I will give you like a little summary, because in this case the bond carbon-oxygen is polar, but the electrons are pulled equally towards both ends of the molecule. So the net result is a non-polar molecule. But what happens if I have, let's say, this molecule? Is this molecule polar? What do you think? Here is hydrogen. And Chlorine is here. And chlorine is to there are two different atoms, right? So it has to be polar. Chlorine is more electronegative. It's a bond between two atoms that are different. So then the bond is polar, the molecule is polar. In the other case, we had this. So the bond is polar. This bond is polar, but it's canceled out with this bond. So the whole molecule, even though the bond is polar, the whole molecule is non-polar. But in this case, the bond is polar, then the molecule is polar. When you have a molecule that, let's say, let's look at this molecule. Okay, let me see. Something, okay. So I have, let's say, let's give you an example. If I have this molecule, well, let's give you a simple one. What is this?
It's water.
Exactly. This is a lone pair, this is a lone pair. When you have to do the Lewis structure first. And once you do the Lewis structure, you're going to end up with this. And this is going to be polar. I think we will go over later because we need to learn the shape of the molecule, how to get the shape of the molecule. And do you know how to, have you seen that in lecture? How are you going to predict the shape of a molecule? Do you want me to go over that?
Yeah, I would like you to go over that because going through the lecture, I didn't learn a lot of this stuff that's actually on the lab and stuff. So
Okay. You will need it to complete this lab. You will have to predict the shape of the molecule. Every molecule, the first thing you have to do in order to predict the shape is to draw the Lewis structure. You will need to know how many lone pairs you have, how many bonds you have. Second step, once you have that, you have to determine the number of electron groups. What is an electron group? You basically count a lone pair, you count it as electron group. So 1, 2, and a bond, you count it as an electron group. So you have 4 electron groups. Now, if you have a double bond, it counts, or a triple bond, it still counts as 1 electron group. And then once you have that, you will predict the shape of the molecule using this valence shell electron pair repulsion. This is a theory that basically says that the electrons repel each other, and they are going to be more stable if they are as far as possible as each other. So in this case, let's say I have 2 balloons, just 2 balloons, and if you do that experiment, the balloons will be happier like a linear, as far as possible. So you will have a linear shape. If you have 3 electron groups, the more stable, this is linear, the more stable is going to be as far as possible. This is 120 degrees. It's called trigonal. I know this is a lot of information. Trigonal planar. It's hard to read. And if you have 4, like we have in here, we have to distinguish between the electron geometry and the shape of the molecule. There are 2 different things. One thing is molecular geometry, and the other thing is electron geometry. So, first of all comes with the electron geometry. This is if we have 4 and the 4 are the same, the electron geometry is going to be tetrahedral. It's going to be something like that. Well, I'm bad at writing. It's going to be 109 degrees. Tetrahedral will be the shape if the 4 are the same. Like if you have a molecule like this, like it's methane, you have 4 electron groups, the 4 atoms are the same. Sorry, I have, can you hear me or I'm gone?
Oh, we can hear you, or I can.
Ah, that's good. That's good. Something weird came in my computer and I thought I lost you. Okay. So this is a lot of information, but we have to look at the electron groups and then for the, so we said that the electron, if we have the electron geometry that is ideal with 4 atoms that are the same, we are going to have a tetrahedral shape. But because in water we have 2 lone pairs and 2 atoms, the shape is going to be a derivative of the tetrahedral. And they are giving you like a little table of, you have to count how many electron groups and how many lone pairs. And then in this case, because the lone pair occupies more space, a bond is shared, this bond is shared between 2 atoms, but the lone pair belongs only to the oxygen. So this atom, instead of being 109 degrees, is going to be less than 109 degrees. And the shape of the molecule is going to be bent. Now, let's see if we can go back to the write-up. So this is the Lewis structure, the molecular shape. And here is what I was saying. All the atoms and electron pairs determine the electron geometry or electron group arrangement, but only the atoms determine the molecular shape, which means it's going to be a derivative of the ideal shape. Let's look at this table, and here they are telling you. This is the basic geometry with 0 lone pairs. When it says steric numbers, is what we counted before, is the electron group, is the steric number. So here this column says 2, means, okay, the central atom is bound to 2 atoms. So here we count one bond 1, the other bond 2. There are no lone pairs. When the steric number is 2, you have a linear shape. Let's look at the basic geometry when you have three. What we have seen, a trigonal planar. But if we have one lone pair, then we have the angle is lower than 120 and the shape is called bent. In our case, we had 4 electron groups. So the steric number is 4. And then the ideal shape with no lone pair is tetrahedral. But in our case, when we look here, we have 2 lone pairs in water. So the shape is bent. If we have one lone pair, it's trigonal pyramidal. Here there is. So this shape is how the molecule is going to be arranged. We look at how many lone pairs, and then you come back to this table. I don't think you need more, but I've seen actually one question. Okay, if the steric number is 4, it's tetrahedral. And then if the steric number is 5, that means you counted the bonds and the lone pairs and you got to 5. The shape is this one. This is the central atom. 2, 3, 4, 5, and I think you're gonna need it in one question. This is trigonal bipyramidal. And then if you have 6, the steric number is going to be 1, 2, 3, 4, 1 up and 1 down. It's called octahedral. This is the shape that this theory of valence shell electron pair repulsion predicts, because they say they want to be the electrons repel each other, so they want to be as far as possible from each other. And they predict these shapes. So this is what is in this write-up. And here there is a, they start with the report, and now I'm planning to go over the report because we saw basically the main theory to complete this. Any questions so far? I'm planning to start to look at the report that you have to complete and make sure you know each step. Okay, so let's start. Okay, so let's start with here. The first thing that you have to do, the first part that you have to complete in the report, ion formation. So they will give you this table and they will ask you to complete it. They give you an example, for example, sodium. So let's see if we can do one more to make sure that you know how to do it. They give you the atomic number. We know where to get it. We go to the periodic table, we locate the sodium, and we write 11. Well, actually, they are giving you that information here. The electron configuration of the atom, we've seen that. Electron symbol with 1 dot for each valence electron. So in this case, we look at the highest number, like in the sodium 3s1, we only have 1 electron in the valence shell, and then we say we do 1 dot. And then gain or lose electron. Obviously, metals are going to lose electrons because the closest noble gas is the number 10, which is neon. And then we say lose 1 electron, and then they say electron configuration of the ion, means when this valence electron is lost, we write everything except the valence electron. So we write everything except the valence electron. The charge +1, the ion symbol, and the ion name. So now I would like to do one more, but I would like you to do it. So let's do, which one do you want to do? Let's put a whiteboard, and
I say we just do the
want you,
next one.
which
Nitrogen.
one?
We'll
Okay,
just do
nitrogen. Okay, so I will put a whiteboard, and we said we are going to do the nitrogen, and we said that the atomic number is 7. So you tell me, the first thing that you have to write is the electronic configuration. Can you tell me what to write?
Yeah, sure. I'll tell you what to write.
Okay.
So to get nitrogen, it's 1s2.
Very good.
And then 2s2.
Very good.
And then 2p3.
Excellent. Excellent. Very good. The second thing is to write the electron dot symbol. So I write the element, and I need to find out how many dots I would do around. How many I need to put?
Now that I'm not sure of.
Okay, we have to put as many dots as the valence electrons. So how many valence electrons are in nitrogen?
Okay. Yes.
John says 3, but the valence electrons are the highest energy level number. So I have a 2 here, and I have a 2 here. I have to add all of the electrons in the highest. Very good. So how many?
So it would be
valence? 5. How many dots do I need to write?
5.
Very good. 1, 2, 3, 4, 5. Very good. We got that. Then they are asking loss or gain of electrons. And how many? How many electrons? If first of all, it is a non-metal, right? And what you have to look is, yes, it is lose 1. John, look at, remember this. Each atom wants to have 8 valence electrons, 8. And they need to reach the closest noble gas. So nitrogen has 1, 2, 3, 4, 5. In order to have 8, yes, gain 3. 1, 2, and 3. This is one way of looking. But the other way is the way as, so for the non-metal, it will be easier probably to say, okay, there are 5, needs to reach 8, the octet, so they need to gain 2. And the metals, it's easier to say the metals always lose, the non-metals always gain. If it's group 1, it's going to lose 1, but the non-metals gain 3. So very good. We answered that question. And then they say electron configuration of ion. So what happened with the ion? It gained 3. Let me write it in another color. It gained 1, 2, and 3. Gained 3. So when I write the configuration, I have to add, if it gained 3, it's going to be nitrogen 3 minus, because each electron is 1 minus. So now I have to write the configuration. Who can tell me what to write? 1s2, same as before, it's always going to be, but because it gained 3 electrons, I need to add 3 more. So 1s2, 2s2, 2p what?
So 2p6 because we're trying to,
Yes.
we're adding 3 to that.
Exactly. And now I have, exactly. Very good. So this is the electronic configuration of the ion. This one. And 3 minus. Very good. And then they ask the ion charge. What is the ion charge? Is this number. Because gain 3 electrons, electrons are negative, so it has a 3 minus. And what is the ion symbol? This, the whole thing. And how do we call the ion? If it's a metal, like sodium, we don't change the name. But remember that the non-metals, that's why you have to be familiar where the metals and non-metals change the ending to IDE. So we call this a nitride. Let me write it. Nitride ion. And that is basically the first thing that you have to complete. Any question?
Yes, so the ion symbol, it would just be what you have right there in green, the N3 minus.
Right, the ion symbol is N3 minus.
Because we're having to add the 3 electrons in order to get us to the noble gas.
Exactly. Ions are always going to have a charge,
Okay.
Positive or negative. Ions means they gain or lost electrons. So you always have to write the symbol of the atom and up to the right, the charge. If we are talking about sodium ion, we are going to say sodium plus because it lost 1 electron. So if they ask you, what is the ion symbol? See, when they give you the example, they wrote this, sodium plus. For us, it's minus because it's non-metal, 3 minus.
Okay.
Okay, so now let's see what else we have to do in the report. Okay, so this part I think is clear. Then they start with ionic compound. We said that ionic is a compound. It's a compound that is made out of a metal and a non-metal. It's a bond between a metal and a non-metal, and they are ions, and it's electrostatic attraction. This one you can complete. They give you like a little picture of how it looks. You don't even need it because it's sodium chloride is table salt, but you can write that they're white crystals, and you can look at the density in Google or the melting point. So this is something just for you to look. What is the appearance of an ionic compound? Then they are going to ask you for the formulas of ionic compounds. So what are they asking here? They ask you, they give you the first example with the sodium chloride. For example, they say, they give you the name, for example, they give you the name, sodium chloride, and they ask you to complete what is the positive ion, what is the negative ion, and what is the formula. Okay, so let's start with let's do the next one. Calcium phosphide. First thing you do, locate both elements. What are the both elements? Calcium and phosphide. Before I will write phosphorus, right? Look at your periodic table and tell me which group is, because you are going to need to write the charge, the ion. Let's start with the calcium, that is the easiest. First of all, it's ionic because it's a bond between a metal and a non-metal. Calcium is a metal, phosphorus is a non-metal. Then we know calcium is going to lose an electron. So what I want to see is which group is calcium? Look at your periodic table.
Group 2.
Very good. Which means what is going to be the charge?
It's just it's gonna have one charge because we're losing one.
Why one?
Because we're losing the other one, is what you're saying?
Yeah, but we said that it loses one when it's group 1. But calcium is which group?
Oh, it's group 2, so it's gonna lose 2?
Yes, it's going to lose 2. Because when we do the electronic configuration of calcium, we are going to know, sometimes in order to abbreviate, we can do the closest noble gas just for me to be faster. So we do the configuration of argon, and then I write calcium 4s2. This is the electronic configuration of the calcium. So the valence electrons are 2. In order to lose 2 valence electrons, that's why it's in group 2. In order to reach the closest noble gas configuration, it has to lose 2 electrons. And then the charge is going to be +2. Does it make sense?
I think, I mean, it's iffy, but
Right, I would learn.
To learn it better.
Yeah, you can actually learn that group 1, actually they give you here, let me see, in the write-up, look at your write-up, there is a place, let me see, that gives you the charges. Is it right, or I'm dreaming? Let me see. Okay, here where it says valence electrons and charges by group. If you look at that table 1, you will see that group 1 is always going to be +1. You can actually learn that easily. Group 2A is going to be +2. So the calcium is in group 2A. You can read again and you will see that chart. It's a lot of information, that's why. And then the phosphide. Which group is phosphide? The phosphorus.
It's group 15, but it's 5A.
Right. Look at that at 5A, which means how many electrons needs to gain in order to have. What did you say?
We would have to gain 5. Is that what you're saying? Or
so
we got to gain 3.
Gain 3. Very good. Okay. So that means.
And because it's going in the equation, it would be a -3 because we're doing the opposite, correct?
Exactly, because electrons are negative.
Right.
So we add 3, 3 minus. And if we lose, it's positive. And now there are many ways of, if it says phosphide and it ends with IDE, you know that is one element, phosphorus, that is in the compound. If it's phosphate, you know that it's going to be another polyatomic ion, but it doesn't say phosphate, it says phosphide, IDE. So the compound is going to be calcium 3, phosphorus 2. That, did you see that in lecture?
I didn't see that in lecture. However, I was reading something. I don't remember what I was reading, but I know we have to do the cross method.
The crisscross, many instructors don't like it, but I think at this point, as long as you know what it means, the crisscross is a shortcut. You use, actually, not even the sign, you use the number 2 of the charge of 1 to put it here. And you use just the number of the phosphorus as a subscript of the calcium. Why is that? Because what happens is that we said calcium 3, phosphorus 2. We said that the calcium has a +2, and we said that the phosphorus has a -3. And you know that the molecule has to be neutral. So they say 3 calcium, calcium 1, 3 atoms of calcium. Each calcium has a +2.
So basically, the reason we're doing that is to neutralize the
Exactly.
or the compound rather.
Is correct.
Okay.
I think I got frozen. I can't write anymore. Okay, now it's coming. Okay, so +2. Exactly. So I have for calcium +6, right? I need -6 from the phosphorus. With 2, I make it.
Yes,
Because
it already has a -3 to it. So
exactly.
multiplying that by 2 and to get the 6.
Exactly.
To make it neutral.
So, exactly. Okay, so this, I think you will be able to do it, right?
Yeah, this part seems fairly easy. So.
Okay, so then ionic compounds. So let's do this one. What do you need to write in? How do I write the positive ion is?
Well, we know in the equation that the positive ion is always the first one.
Right. So I write sodium. And how many charges? Which group is that?
Sodium is in group 1.
So then it's +1.
So then it would just be a plus.
Yes. How about nitrogen?
Nitrogen is group 15 or 5 electrons.
So it needs to gain 3, right?
So to gain 3 in order for us to get to neon.
Exactly. And how are we going to call this compound?
Give me 1 sec. Let me think about it. Nitride. So it would be sodium nitride.
Very good. IDE. Now tell me, what is the charge of here, aluminum, of this, for aluminum? What is the charge of aluminum?
For which? Okay, for aluminum. Well, it's in group 13, but it has to -5 to get to argon. So, would it be Al5 minus?
Look at the periodic table.
Right.
And you said that you need to gain 1, 2, 3, 4, 5.
Correct.
But if you go to the previous noble gas,
Oh, it's because, okay, it's closer to that one. Okay, so we have to add 3 to it then.
it has to lose, right?
Yeah, it has to lose 3. So that would be it's still the positive because it's first. So it would be
Yes.
Al 3 plus.
Very good. Oh, exactly. You look at the closest.
Yeah,
And always, that's okay. And always remember that metals will be positive. Non-metals will be negative. So here it says positive ion because it's the first element. The second is the non-metal. It's going to be negative. Does it make sense?
Yeah, I think it makes sense now. I'm just gonna try and finish this one that we just started, the aluminum chloride,
Okay.
and then I guess we can move on after that, or if anybody else needs help.
Okay. Yes. So what is the negative ion here?
So I believe it's just we have to get to 1. So from 17 to 18. So then it would just be Al 3 plus and then Cl negative, and then it would be
Very good.
called aluminum chloride.
Yes, exactly. Because aluminum is always +3. Very good. And then they talk about what else? Formulas of ionic compounds. Let's do silver sulfide, the last one. What is the formula? Or let's do a whole thing. What is the positive ion?
The positive would be the silver.
Silver. And what is the charge?
Let me see.
This is one of those that you have to learn. It's always +1, silver.
Okay.
You cannot guess, actually. It's one of those exceptions that it's always +1. And sulfide, that one you can guess.
Will it just be, since there's no numbers following in it, is it just negative?
Negative what? How many electrons needs to gain?
Oh, it needs to gain 2. So
Very good. So it's going to be 2 minus.
2 minus, yes.
2 minus, because it needs to gain 2.
Right. So then it would.
And the formula.
It would look like
Silver.
Ag2 S.
Very good. Exactly. Very good. And then names of ionic compounds, that this is the same, but you need to include the Roman numbers.
Yes. So when we're doing that, how do I determine the exact Roman numeral it's going to be?
Okay. So you don't know actually the what you know is the anion, what is the charge, right?
Mm-hmm.
Let's do this one that is a little more complicated.
Okay.
So let's look at this compound. Has 3 oxygen. So you know that the molecule is neutral, right? And you know the oxygen is always going to be -2 because it's in group 6. And then you have 3 oxygens. So the total negative charge is -6, right?
For oxygen, is that what you're saying?
Yes, for
Because we have
oxygen.
3, and each
That's,
one has to get 2 subtracted from it to make it to the closest noble gas. So yes, so that makes
the
sense.
the oxygen, yeah, needs to gain, but you can actually learn it like, okay, everything in group 7 is -1. Look at that in the write-up. After all these workshop, I think once you read it again, it will be fixed. You will grasp it, because if you look at so you don't have to think each time. You will say, okay, group 7 is always -1. The group of the oxygen is always going to be -2. The group of the nitrogen is always going to be -3. It's going to help if you are running out of time. So the oxygen, we said -2, but we have 3 oxygens, so it's -6, which means that the positive here is going to be +6, right? But I have to, in order to be neutral, it has to be +6, but you have 2 irons. So when you divide by 2,
It's 3.
it's +3. Each iron has a +3. And then you know that the Roman number is 3. So
Oh.
the number of the compound is going to be iron, then the Roman number 3, and then you're going to say oxide.
Right. So with that, will it always be like the number following the second element? So for
Right.
with
Yeah,
the
sure.
one down, the CuCl2, would it be what is Cu? The element for Cu, and then that would be to the Roman numeral of 2 because of the 2 there, or will it be like,
Yes, very good. Because you have 2 chlorides, so the charge of this part is -2, right? So
right?
the copper has to be +2. Very good. So the compound is going to be copper, Roman number 2, chloride. So basically, when you have transition metals, you have to start from the anion that you know the charge. Yeah, it's a lot. I don't know why they did so much info here, but yeah. And then polyatomic ions. Okay, this is just a description that you are going to look at your picture. You're going to say this is a white solid and look at the information there. And then formula of ionic compounds. So this one is what we have seen so far. Let's do one. What is the formula of lithium phosphate? You know, lithium is, you look for the lithium is group 1, is +1. Phosphate is one of those polyatomic ions that you need to learn, and is -3. So there is no way you can just figure it out. You have to learn, yeah, that phosphate is that polyatomic ion. And then when you write the compound, you are going to say, okay, lithium 3 phosphate. Does it make sense?
Yes, I believe it does make sense. It's just going to take a little bit to get the hang of it.
Yeah, it takes a lot of practice. It does. And then if you have, in this case, the phosphate, you need just one because lithium is +1. But if you need more than one, you have to put a parenthesis. That's all. And then names, same thing. You will have to learn the name, like this is sulfide, and you're going to say, okay, this is potassium sulfide, or you will need to learn, they give you the list. So this is phosphate, and so you will, this one I think is the same as what we have seen. It's just that you will need to learn those polyatomic ions. And then comes the water. You write the appearance of the water, the density, and here is what we have seen about molecular compounds. When you have a compound that is in between two nonmetals, you have to use those prefixes. So basically, they give you silicon tetrachloride, and you have to write the formula. This is much easier, I believe, than the ionic compound. You just have to look at the elements first, so you know it's going to be silicon. And tetra, you need to learn the prefixes. It means 4. So you are going to have 4 chlorides. And that's how you are going to complete this. And then the name the same way. And here is what I was talking about, how this is hard because this is what we have seen to write the Lewis structure, then find out the steric number, the electron group arrangement, and the molecular shape, and if it's polar or not. So let's do one before we conclude, and then I'll stay to answer questions. Which one you want to do?
I know we've already done water, so let's just try the is it what, silicone bromide?
Okay. Yes. So first of all, silicone bromide. The first thing that they ask is the electron dot, the Lewis structure, right?
Right.
So when you do the Lewis structure, you basically count all the electrons. Silicon has 4, because when you look, it's in group 4. It's underneath carbon.
Yes.
So it has 4 valence electrons. So you count 4 from the silicon plus bromide has 7. It's a valence 7. And you have 4 bromides. So it's 4 times 7. So basically, you have 32 electrons. And then you start by writing the first element in the center, and you write, you have to bond them because it's a molecule. So from the 32, you needed 4 bonds, which is how many electrons?
Wait, can you say that one more time? I'm sorry.
Yeah, so basically you wrote the 4 bonds because the silicon is bound to 4 bromides. How many electrons did you use for those 4 bonds?
So for the 4 bonds, I used 4 for the, because I
each bond is 2 electrons.
Each bond what? I'm sorry.
Each bond is 2 electrons.
Okay, so then we used 8.
8. So I had a 32 electrons total minus 8. How many I got? 24 electrons, right?
Correct.
Left. And I start by completing 6 electrons in each bromide to complete the octet. That way, each atom has 8 electrons, even the silicon in the center. So this would be the Lewis structure. What is the steric number? I count 1 each bond, and I have to count 1 for each lone pair.
Okay, so where you're getting the 2 is the bromide counts as 1 itself, and then the line to it counts as 1, and that's why there's only 6 dots around it. Is that correct?
No, sorry. Now I finished like the Lewis structure.
Mm-hmm.
Now what I'm trying to do is look for this steric number. Steric number is, I know it's a lot, it's what we have seen. We count how many electron groups are around the central atom. And the central atom is silicon.
So we have 4 groups around it.
Exactly. The steric number is 4.
Okay.
If I have a lone pair, like let's say in ammonia, how many electron groups I have for nitrogen?
We have 3.
Because I have to count a lone pair as 1. So the steric number for nitrogen is also 4.
Because you're still having to count nitrogen as a pair.
Because I have to count. So let's see. Nitrogen, let's say the Lewis structure of nitrogen is this one. And I have to find out the steric number. Steric number is counting each lone pair in this. I have to look at the central atom, which is nitrogen. Each lone pair counts as 1. Each bond counts as 1. 1, 2, 3, and 4. So the steric number for ammonia is 4. In this case, we don't have lone pairs, so we don't count. Does it make sense?
No, not really.
No, this is a concept that is a lot, it's a whole chapter. So I'm not sure if you are going to study that in or not. Because for lab, we are not, I don't want to get into too much detail if you don't need it.
Right. But
So,
obviously we're going to need something with this because it's on our lab.
Exactly. So what I would say is, for the steric number, look at the central atom and count. After you do the Lewis structure, count each bond as 1, each lone pair as 1. So the steric number is 4 because the central atom has 4 bonds.
The silicone has 4 bonds for this.
Exactly. So let's look, when you do the Lewis structure for this one, you will end up with something like 2 lone pairs, 2 lone pairs. So you will have 1 lone pair, another lone pair, and 2 bonds to fluor. And what is the steric number there?
Wait, what? I guess I'm a little confused on the whole
I know.
process of the Lewis structure, because I'm not understanding why. So why for the SF2, why is S going in the middle? Because it's the first, or it's because it's the
Yes,
line?
the first element usually is the central atom.
Okay, so that's why we got that. Now
Yes.
the dots that you have underneath the sulfur,
Yes.
where are you getting those from? Is that from the
Okay.
electrons that are needed?
Is exactly when I didn't do step by step, but when you do the Lewis structure, you have to count at all the electrons. So you will have 6 electrons from the sulfur plus 7 electrons from one fluor plus another 7 from the other sulfur. So you will have 20 electrons.
Okay,
And
let me try
then
and catch up with that real quick. So you're getting 6 from the sulfur because it's 2 to the nearest noble gas, and we have to multiply that by 3 because of the
no. Where do you see the 2? Do you see the 2?
the reason I'm getting 2 is because the S is 16 on the periodic table elements, and it needs 2 to get to the noble gas for more electrons. Is that something different?
Yes, that's different. That will be the charge of the ion. But in this case, we don't have an ion. We have a covalent bond. And we are just looking at the valence electrons. So the sulfur is in the group, you said 16. Try to not to look at the first number and say group 6, because 16 is correct when they are considering there are 2 ways of naming. If you ignore the transition elements, you end up with group 6. And it's easier to remember that it has 6 valence electrons.
Right, I see now. 6A, so it's 6 valence electrons, and 7A would be 7 valent electrons.
Right.
Okay.
So then you have, this is, you can look it up. I mean, I think in the write-up is clear. When you read it again, I feel like you are going to grasp it. For now, this is the way, it's hard to memorize how to write a Lewis structure just by one workshop. I was assuming actually that it was done a little bit in lecture. So the lab is not very much coordinated with the lecture, but so that's why you have a lot to learn, but you will grasp it. But for now, these are the steps on how to write the Lewis structure. So 6 is the 6 valence electrons, and 7 is because it's in group, fluor is in group 7. So we have a total of 20 electrons. And the next step to write the Lewis structure is to write the first element as the central atom, and then we bond it to the other element. And you start by counting how many electrons you use in the bond, and then you subtract that, what we did before, and then you start adding all the electrons on the surrounding electrons, which is fluor. And here I ended up with 2 lone pairs because I had extra electrons. So you start in the fluor, and if you have extra, you go to the central atom.
Okay, so it's a little hard to see how many dots you have on the fluor.
I know. Let's erase everything. Okay.
Can we go to the whiteboard to make it bigger?
Yes,
Okay.
let's do that. Okay. So basically, what are we trying to do? We are trying to do the Lewis structure for this compound, right?
Correct.
First thing we do is calculate all the valence electrons. And we look at sulfur and we say, oh, sulfur is in group 6, 6 electrons. And then we say fluor is in group 7. I have 2 fluors, so 7 plus 7. Each one has 7. So I have a total of 20 electrons. This is the first thing I do. Second thing, the first element is the central atom. So because I have a molecule, I have to start with a single bond. And now, from the 20 electrons, I already used how many when I did these 2 bonds?
I believe 4,
Exactly.
because it's 1 for each F, and then the dash counts as 1 as well. Is that?
Is because each bond, each line is equivalent to 2 electrons.
Okay, so the F actually means nothing right now, but the line is equivalent to 2 electrons, and
Right.
that's in every equation for this setup.
Yes.
Okay.
Each bond that you do, if you have 3 atoms, you have to connect them with 3 bonds.
Correct.
So then you use 6 electrons. But in this case, I have 2, so I only need 2 bonds. So I have 16 electrons. And I always start in the surrounding. And I need to start using all those 16 electrons. I start with the fluor, and the fluor needs 6 to complete the octet. 2, 4, 6, plus the bond that is sharing, 8. Then I go to the other one, 6. I already used how many electrons? 6 on one fluor, 6 on the other.
So plus so 12, it's 16 total right now.
16. And how many I used when I added to the fluor?
You used 4.
So I used 4 for the bonds.
Okay.
But then I started to use these 16 electrons when I try to field the electrons around the fluor.
So right now we have 12.
Yeah.
12 around the fluor.
Very good. So how many electrons I have left?
Out of 20 plus, so 12 plus the 4 that it takes.
No, I already used 4. So I had 16. How many I use in the fluor?
You used 12, so we have 4 left.
4 left. Because I don't have more atoms around, the last thing I do is I place it on the central atom.
Okay.
And that's why I ended up with this. This is the Lewis structure. And then, in order to know the shape of the molecule, what I do is count. I have to find out that steric number. Steric number, I have to count each lone pair as 1. I look at the central atom. The steric number is for the central atom. So I look, each lone pair counts as 1. Each bond counts as 1. It doesn't matter if it's a double bond or a triple bond. Each bond from the central atom counts as 1. So how many electron groups, counting the lone pairs and the bonds, I have?
So you have, I would say 4 because of the 2.
Oh, exactly.
The 2
Very
groups
good.
that are attached to the, yes, and then the other 2. Okay, yes.
So and then I go to that table that they give you, and the ideal geometry for a steric number 4 is tetrahedral, the ideal.
Okay, so then in the electron group arrangement, that's where we would put the tetrahedra, or whatever the number of the steric number correlates to. So if it's 5, it'd be whatever the 5 is.
But when you look at the table, you have to look within tetrahedral, because the 4 electron groups are not the same atom. There is a table that says that if you have 4 steric number, but you have 2 lone pairs, the molecule the shape of the molecule is going to be bent.
Bent or angular. Got it. So then when we draw it, it wouldn't be in a linear format. It would be in that format right there. That bent.
Exactly. Yes. Awesome.
Okay.
Exactly. That's why it's important. You cannot avoid doing this Lewis structure, because the lone pairs will give you, if you don't write it on the central atoms, you are going to obtain the wrong shape of the molecule.
Right.
And then I believe that we are at the we can conclude this, but I will stay to answer all the questions. But I want to make sure that I'm not forgetting anything. I think we got to the end of the so this is the table that I give you, that it says, okay, the steric number is 4,
Right.
but we had 2 lone pairs, so our shape is this. So this is what we have to use, and I believe yes, and I think this is a good time to stop. I will stop the recording. I want to thank you for coming, and I will stay to complete all your questions. Thank you.